Hello everyone, I'm Mengyuan from the National Space Science Center and the Albert Einstein Institute in Hanover. Today I will give you an introduction on the simulation of diffracted light to show some of the open challenges and introduce my work on the extensions for the diffraction simulation. The space gravitational wave detectors, such as LISA and Taiji, has very strict precision requirement, so it's necessary to test and validate the expected performance of the laser interferometry by optical simulations. What I'm investigating now is the extension for the diffracted light simulation methods. There are some open challenges, mainly including optimal settings and the fair comparison, which I will introduce in detail later. But first, let me give a brief introduction on the diffraction simulation. The diffraction in the Taiji and LISA, mainly including the received beam from the far spacecraft clipped by the telescope and the local beam clipped by the optical components in the optical bench. There are many methods for simulating the diffracted light, such as MEM, GBD, or using integration methods. But what we use in the LISA and Taiji optical simulation are the MEM and GBD, because they are easier to use in the complex optical setups compared to the integration methods. The MEM and GBD has very similar principle. We already know that propagating the plane wave and various description of laser light are easy, but propagating arbitrary wavefront are difficult. So we can compose the field into a superposition of the fields we know how to propagate, such as the Laguerre Gaussian modes or the fundamental Gaussian beam. Now I will give a brief introduction on MEM. MEM decomposes the incident beam into a superposition of higher modes, such as the Hermite Gaussian mode or the Laguerre Gaussian mode. This figure shows the transversal intensity distribution of higher modes, and here is the setup of the MEM. The incident wavefront is clipped by the aperture in the aperture plane and decomposed into higher modes after a propagation of some distance. The electric field is calculated as the superposition of these higher modes on the observation plane. This equation shows how to calculate the electric field of the superposed beam. As I mentioned before, both MEM and GBD are decomposing the arbitrary wavefront into a superposition of some description of the laser light. The GBD tells another story. It decomposes the arbitrary wavefront into fundamental Gaussian beams on a grid. This is the initial wavefront. These small circles are the fundamental Gaussian beams. The electric field is calculated by the superposition of these small beams. Now we need to make a fair comparison of MEM and GBD because we want to know if both simulations run for the same time, which method is more accurate. Firstly, let me show you an example of the comparison. The upper figure shows the amplitude, phase, and the error of both MEM and GBD in the 5 mm distance after the aperture, and the lower picture shows the same thing for 10 mm distance after the aperture. The settings of the comparison are in the red table. With such settings, GBD runs better than MEM in both computational efforts and accuracy. But this is not always true. There are other settings MEM behaves better than GBD, so a more general comparison still needs to be performed. But how can we choose the settings? For MEM, we need to consider the decomposed beam width and the mode order. But now we only know how to choose these settings for special cases, such as a plane wave clipped by a circular aperture. For GBD, we also face the same problem. We need to choose how many beams, in what shape should the grid be arranged, and the beam parameters. but now we only know some settings for special cases. Before we can make a comparison, we need to know how to choose these settings for general cases. My work is mainly about finding the optimal settings for MEM, so I will introduce the current status and my work now. Bogey gives optimal decomposed beam width for given mode order n. However, this only for a plane wave clipped by a circular aperture. Is not a suitable assumption in LISA and Taiji in the following two cases. So I will extend the optimal settings for the clipped Gaussian beam. Now I will show my work step by step. In Bogey's paper, he gave this equation. The decomposed ratio is a function of n, but this is only for a plane wave clipped by a circular aperture. For a clipped Gaussian, we need to consider the incident beam width, and the optimal decomposed ratio is a function of the incident beam width, mode order, and the aperture size. The first thing I did is to check the linearity of the incident ratio. To make things easier, I found that the incident ratio has linear effect on the error function, as shown in this picture. The x-axis in this figure is the decomposed ratio, and the y-axis is the error. You can see, even if the aperture sizes and the incident beam widths are different in the 5 different cases, but they have the same error. So we can simplify the variables of the function f. We don't need to consider the 3 variables. We only consider these 2. Next, I decided the clipping boundary to define the different clipping cases. If the incident ratio is smaller than 1/3, there is no clip, so the optical decomposed ratio is equal to the incident ratio. We don't need to decompose beams because they are not clipped. If the incident ratio is between 1/3 and 3, the incident beam is a Gaussian beam. Its complex electric field distribution is shown in this picture. The optimal decomposed ratio can be given by a function f, which is needed to be found out. And if the incident ratio is larger than 3, the incident beam can be regarded as a plane wave, as shown in this picture. So we can use Bogey's result. To find the function f, I plotted the error function in 2 different aspects. In the left picture, it shows that the error functions of fixed incident ratio for different mode orders. The x-axis is the decomposed ratio, and the y-axis is the error. You can see that with the increase of the mode order, the error becomes smaller and smaller. You can also see that there is an optimal for beam parameters in the decomposition. You can also see that the error only slowly decreases with an increase of the mode order. This is very important because we can use less mode order to save time, but we don't have to lose so much accuracy. Additionally, you can see that there is a range of choices which is not ideal, but still quite usable. I call it bucket size. And the right figure shows the functions for different incident ratios with fixed mode order. The x-axis is the decomposed ratio, and the y-axis is the error. You can also see that there are optima in each curve and the bucket size. Here, the function f can be found out by fitting the optima for each error functions with different mode orders and incident ratios. And the way is the same for finding the bucket size. Let me make a summary of my report. We need optical simulations for Taiji and LISA to achieve high accuracy, but such simulations are complex because of the presence of diffraction. Here, introduce two methods, the MEM and GBD. They are easier to use in the LISA and Taiji simulations than the integration method. Currently, it's not clear what settings are optimal, which can result in higher accuracy for lowest runtime. So I have started an investigation on runtime comparisons, and I have shown optimal settings for MEM in the plane wave clipped by the circular aperture case. And I also have started the investigation on the optical settings for the clipped Gaussian beam. However, this work haven't been finished, and I will continue to find the optimal decomposed ratio and the bucket size, so that the fair comparison can be made. Alex and Yuzhu's presentations are related to mine, so if you are interested, you can also watch their videos. This work has been supported by the CAS and the MPG in the framework of lexical operation on low-frequency gravitational wave astronomy. Thank you very much for listening.